My name is Professor Prof Orata. We are continuing with our thermodynamics lectures. Today we look at thermochemistry. And if you remember from our earlier lectures, we developed two relationships relating state functions to thermochemical observables, or what we call path functions, that is heat, and thermodynamic state functions H and U. That is, we have said that dH is equals to dQp and du is equals to dQv. That means that heat transfer under constant pressure is the same as the change in enthalpy, and the heat transfer under constant volume is the same as the change in internal energy. Now, these are thermochemical observables. These are thermochemical observables. Thermochemical observables. And these are thermodynamic state functions. State functions. Now, we said that Q and W, which are path functions, and this particular case, a thermochemical observable, depend on the path which you follow during the process. Whether if it's adiabatic, then there's no heat transfer between the system and the surroundings, so Q is 0. If it's non-adiabatic, then Q will have some value. And when we talk of thermodynamic state functions, we said one, they depend on the state of the system, and they are exact differentials. So in the earlier lectures we showed what exact differentials are. So this link between thermodynamic state function and thermochemical observable is critical in thermochemistry. And you notice that in most of your studies, you will see that we use a lot of delta H as opposed to delta U. And this is for a very simple reason, that dealing with constant pressure is a lot easier than dealing with constant volume. Like when you look at the earlier lectures where we talk of bomb calorimetry, we have a specific unit which is a constant volume bomb. But when you're dealing with constant pressure, if you're doing experiments under ambient conditions or atmospheric conditions, then the chances that the atmospheric pressure will vary significantly is very limited unless there's a very drastic change in the weather. So you can still obtain the value of delta U from the relationship H is equals to U plus PV. So if you know delta H, you can still obtain delta U from the relationship delta PV. I need to emphasize here that this delta PV is not necessarily nRT. nRT is only if it is an ideal gas. It's behaving like an ideal gas. That means it's obeying the equation of state PV is equals to nRT. And if that is the case, then delta H will be equals to delta U plus delta N gas RT. And so you look at the changes in the number of moles of gaseous phase from your reaction stoichiometry. So it's very important to note that it is very easy to move on to calculate delta U once you know delta H. Now, when we are dealing with thermochemistry, you must be very, very certain about what reactants are and what products are. C plus D. So, these are reactants, we call those our reactants, and C plus D are our products. C plus D are the products. So, when you are computing the enthalpy change for a reaction like this, the enthalpy change, delta H, for this type of a reaction, is given by the sum of the enthalpies of the products minus the sum of the enthalpies of the reactants. And in most cases, we talk of under STP, standard temperature and pressure conditions, so we'll have theta there to indicate that we're dealing with systems under STP. So delta H theta will be given as the sum of the products. In this particular case, it will be the enthalpy of A plus enthalpy of B minus the enthalpy of C plus enthalpy of D minus the enthalpy of A plus the enthalpy of B. Now, when we are using enthalpies or internal energy, which are state functions, we can apply Hess's law. We can apply Hess's law. We can apply Hess's law. And what is Hess's law of constant heat summation? Hess's law of constant heat summation means that you can actually add these reactions. Suppose we have, let us start that Hess's law. Hess's law means that if you have A plus B going to C plus D, that is reactants A plus B forming C plus D. And another set of, let's say that the delta H for this reaction is delta HX. And then for another reaction, let us say D plus E forming B plus M. And the enthalpy change for that reaction is delta HY. Now, since H is a state function, depends only on the initial and final values of the state of the system, we can actually add these two reactions so that we have the net reaction where now the D will cancel with that and the B will cancel the other B. So we have the net reaction is A plus E forming C plus M. And what about the enthalpy? You simply add them. So for this reaction here, let's call the enthalpy is H, delta HR, will simply be delta HX plus delta HY. And it simply means that we only are interested in the initial state, that is the reactants, and the products. So that even if there was another primary reaction in the system, let us say we had Y going to M and M going to Y, and each of these as their enthalpies as DH1, DH2, of course they have cancelled out. So even if you had those systems there, it doesn't matter how many reactions you have. What matters is what is the reactants and what are the products. So even if you have 100 reactions which you have added together to get this net reaction, when you add the enthalpies, the values will still be the same. And that's the beautiful thing about the Hess's law of constant heat summation based on these particular state functions. Now, these reactions are very, very important that when you are dealing with thermochemistry, it's important that when you're dealing with thermochemistry, you specify the stable state of aggregation of your chemical species. For example, if you have a reaction involving carbon solid plus oxygen gas to form carbon dioxide gas, the stable state of aggregation is solid for carbon, gas for oxygen, and gas for carbon dioxide. Now, this type of reaction, of course, if carried out under STP, will be a formation reaction. The formation reaction of carbon dioxide. And that carbon dioxide is being formed from its elements in their standard states. It's formed from its elements in their standard states. So we have that this will be the enthalpy of carbon dioxide and the standard state minus the enthalpy of carbon solid plus the enthalpy of oxygen 2 gas under STP. Now, the enthalpies of the elements, note that the enthalpies of the elements are taken as 0, assumed to be 0. The enthalpy of the elements are assumed to be 0. So what do we have? The enthalpy of formation of carbon dioxide, the enthalpy of formation of carbon dioxide is the same as the enthalpy of carbon dioxide. This is a very important point to note, so that when you go to the handbook, where you're going to look for the values of the enthalpies, if you're looking for the enthalpy of a compound, look for its enthalpy of formation. So the enthalpy of a compound is the same as its enthalpy of formation. That's very important for you to know. We can have other reactions. We can have other reactions also. We can have other reactions like an hydrogenation reaction, a simple Markovnikov reaction, where we have an ethene being hydrogenated to to form ethane. We can call that enthalpy of hydrogenation. Again, under standard conditions, theta, so we have some value there. Again, you take the enthalpy of ethane minus the enthalpy of ethene and of hydrogen. Remember, hydrogen is an element, so that will straight away be 0. Of course, you will have to balance your equation so that you must always have your equations stoichiometrically correct. So in other words, you must always balance your atoms. Very important for us to note that. Another hydrogenation can be that of benzene, which you are familiar with. You can have benzene hydrogenated to form cyclohexane, and so forth. Again, that's still the enthalpy of hydrogenation. This is of ethene, this one is of benzene, hydrogenation, of benzene, and so forth and so forth. So it's very important for us to take note of that. Even hydration of a salt like copper sulfate has an enthalpy change. So it's very, very important for us to know those kind of reactions and how we can express their enthalpy changes in those particular reactions. Now, we want to move on to mention a few things in terms of exothermic reactions. If we have that reaction, again, A plus B, going to C plus D, and we find that when we take the enthalpy change and the standard conditions for the products minus that of the reactants, we get a negative value. Then it means that reaction involves evolution of heat. So it is an exothermic reaction. Similarly, endothermic reactions are such that A plus B, once again going to C plus D, is such that delta H, the change in enthalpy, is, as we have said, that enthalpy for the products, sum of enthalpy of the products minus sum of the enthalpy of the reactants will give you a positive value. That's an endothermic reaction. In other words, that's a reaction which requires heat to be supplied into the system for it to proceed in the direction of forming the products which you desire. Now, what is the significance of this? If you are a scientist or an engineer and you're dealing with a process, a reaction, and you don't know whether it's exothermic or endothermic, then you can see the danger which is there. You end up mixing some chemical substances and you end up with a lot of heat generated. And of course, pressure will build up and that can be quite catastrophic. So, as a scientist or an engineer, you must know what kind of reaction are you dealing with. Is it endothermic? Is it exothermic? If it is endothermic and you didn't know that, then you will put your reactants together. There will be no reaction. You will wait indefinitely. There will be no reaction because you need to inject heat into the system. And if heat is released, a lot of it, you as an engineer or a scientist, you need to know that in that particular case, you not deal with a batch reactor, you need to deal with a continuous tank reactor where you have your batch there, your reactor there, but you lag it. In other words, you are able to circulate, for example, water into the system. You can, so that it cools your system. So that water in, for example, water out. And of course, you have your batch reactor here where you are having your reactions taking place. So this is very important so that it dictates what type of a system you deal with. Now, suppose you are dealing with a system. Let us say you are dealing with a system like a geothermal. You are in a geothermal plant where the temperatures underneath the surface of the earth are very high, and of course you want to generate your steam and use them to produce electricity and so forth, your thermal plants. And so you will be talking of what is my enthalpy, because when you talk of enthalpy under STP, that is normally at 298 K. We are talking of 298 K, but that might not be the situation underground. The temperatures might be thousands of Kelvin. So how do you know what will be the enthalpy? Enthalpy is involved. So this is very important for us in terms of use of Kirchoff's equation. I don't want to call it Kirchoff's law because there's Kirchoff's law in electronics. So I'll just call it Kirchoff's equation. And so we just start from the first principle. If you look at our earlier lectures, we saw that dH by dP, that gives you the isobaric heat capacity. And so if there's change in enthalpy d delta H, dP, then there will be change in heat capacity. Now, that delta Cp should not scare you. It's the same thing, just like delta H. Delta Cp is simply the sum of the heat capacities of the reactants minus that of the products. Heat capacities, just like we did with the enthalpies. So you sum the heat capacities of the products, subtract that from that of the reactants, that gives you delta Cp. And then you plug it in there. You plug it in there, and you should get a value. But remember also that sometimes, important to mention, sometimes you will find that the heat capacity has a strong dependence on temperature, and it can be expressed in a series form. Cp is equals to A plus B, T plus Ct squared. Plus, plus, plus. You truncate it at the point where it gives you the most accurate value for your Cp. Now, when you see this, again, that should not challenge you much. All it means is you have to do a lot of bookkeeping, so that you subtract the A's for the product from the A's of the reactants. You deal with the BTs of the products and that of the reactants, and the Ct squared, the products and that of the reactants. So the challenge is just the bookkeeping. You don't confuse where you subtract the A from that of the BTs and so forth. So that's very, very important for us to note. Now, if we integrate this particular quantity, so we have d delta H as being equal to delta Cp dt. Integrate from some limit, some initial value to some final value, initial value, final value. I am assuming is an initial value, and f is a final value. Remember, in the early lectures, we say that if you don't put those limits, then you have to put in the integration constant in whatever you get. Now, when you integrate this, I'll just use the simple integral calculus identity. That's the integral of dx is simply x plus an integration constant. So the integral of d delta H will simply be delta H. Will simply be delta H from initial to final value is equals to delta Cp into T, some initial, some final value. So if you open up this expression here, we have delta H at Tf minus delta H at Ti is equals to delta Cp into Tf minus Ti. This expression you see here is Kirchoff's law, or Kirchoff's equation, like I said, because you don't want to mix up with that of electronics. So what does that mean? You want to know what is your enthalpy at some ridiculous temperature or some unknown temperature which is not captured in the handbooks. But you have a base value which you can refer to, that is your delta H Ti is what we have as your delta H, some standard conditions. So that serves as your base for that. You know what is your temperature for that particular base, and you know the temperature which whose value you do not know the corresponding delta H. So you are able to obtain the values, just put in the value from the handbook, that is for the delta H, and you know the two temperatures, and you're able to come up with the value for your enthalpy at whatever temperature you are interested in. That's very, very important for us to note. And again, if delta Cp depends on temperature, then that integral expression now changes significantly. So that what we'll have now, if the temperature, if the heat enthalpy, heat capacity is dependent on temperature, then we'll have the integral again from I to F is given as A plus BT plus plus Ct squared. Let's say we have truncated it as a third term. So you have IF dt. So integrating these quantities, we get again delta H at Tf minus delta H at Ti. Ti is equals to the integral of A dt plus the integral of Bt dt plus the integral of Ct squared dt. So all that will come to At plus Bt squared over 2 plus Ct cubed over 3. Then of course you plug in the values. So you'll have that as A of Ti plus B of Ti squared over 2 plus, that's the final, we want to talk of the final quantities, Tf and Ctf cubed over 3 minus A Ti plus B Ti squared over 2 plus C Ti cubed over 3. And that will give you the value, where in those cases where the heat capacity is strongly dependent on temperature. And this heat capacity is very, very important that you note for your system, so don't always assume that it is constant. You must find out whether your heat capacity requires that you factor in the temperature effects or not. So this type of a system, like we have said, revolves on the simple fact that enthalpy is a state function. And that's how you compute even the enthalpy of the crystal lattice, for example, for sodium chloride, which you did in the freshman courses, which was the basis of the Born-Haber circle. But the Born-Haber circle, you had the atomization of sodium, the dissociation of chlorine, and then you had the ionization of sodium to form the sodium ion, and the electron affinity, where electron is pumped to the chlorine to form the chloride ion, and then of course they combine, and that gave you the enthalpy, the formation of the lattice for sodium chloride, which is a very strong, nice, hexagonal, close-packed structure. So we can stop at that particular point, and then we'll pick up on the other next lectures in the next series.